Hello friends, welcome to my YouTube channel. Today we are going to show that space-time interval is invariant under Lorentz transformation. Right, so we're gonna prove this that space-time interval, this is invariant under Lorentz transformation. So before we start, please subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID, Oza Likhajit LAKHYAJIT 123. This is my Insta ID. You can follow me on Insta. So now let's start. First, let me consider two frame of reference. Let us consider two frames. One is this and another is this, suppose. Right, these are two frames. So this is suppose frame S and this is suppose frame S dash, and this frame is moving with velocity v with respect to this frame, right, along x-axis. So just wait. So S dash is moving with respect to S along x-axis. Let me consider that way. So this is the origin here, origin O this, right? So let us consider two events, E1 and E2. Right? These are two events. Okay, we want to find the space-time interval. Okay, space-time interval, because coordinates of any event in space is represented by x1, y1, z1 and t1. So here it is considered to be four dimension, and fourth dimension is the time. Okay, x, y, z are the three dimensions, then the fourth one is time. Okay, similarly for this event E2, we're gonna take x2, y2, z2 and t2, right? And according to this frame of reference, their coordinates will be again different, x1 dash, x2 dash, like that we're gonna consider. So I'm gonna write here, just I'm not gonna mention these coordinates here because there is not enough space. Okay, so but I will mention here, just wait. So let us consider two inertial frames, S1 and S and S dash. Okay, and the frame S dash is moving along x-axis with velocity suppose v, right, with velocity v relative to s, right? We have taken that way. Let us consider two events. Let E1 and E2 be two events and their coordinates in S frame are, suppose E1 is x1, coordinates of E1 is suppose x1, y1, comma z1 and t1 in S frame, and coordinates of E2 the x2, y2, z2, t2, right, respectively. And in the frame S dash, okay, E1, its coordinate is suppose x1 dash, y1 dash, z1 dash, right? Z1 dash and T1 dash, let me take that way. And coordinates of E2, so x2 dash comma y2 dash comma z2 dash comma t2 dash respectively. Okay, let me take that way. Now you see the space-time interval in S frame. Okay, so how to obtain that one? So here you see, actually this is known as space-time. Okay, this is a 4-dimensional coordinate system. This is known as space-time. Okay, so an interval between these two is known as space-time interval. Interval between these two events, right? So let me consider that del S is the space-time interval. Space-time interval in S frame. In S frame, and del S dash, be the space-time interval in S dash frame. Okay. So we're going to show that here we are to show that del S square is equal to del S dash square, okay, under Lorentz transformation, right? Under Lorentz transformation, right? Sorry. Okay. Now let me take a new slide. Take the screenshot. Okay. Take the screenshot. So here you see. So these are the two frames. Here this is the event E1 taking place. Here is the event E2 is taking place, and this is the S dash frame which is moving with V, velocity V along x direction, right? So now you see this del S square will be given by del X square plus del Y del Z square minus C square del T, right? And del S dash square is given by del S dash square is given by del X dash square plus del Y dash square plus del Z dash square minus C square del T dash square. Okay, now you see what does del X del Y mean. Here let me write del X means x2 minus x1, that means interval along x-axis. Similarly, del Y means y2 minus y1, and del Z means z2 minus z1, and del T means t2 minus t1. Similarly, del X dash is nothing but x2 dash minus x1 dash, x2 dash minus x1 dash. Similarly, del Y dash is nothing but del Y dash is y2 minus y2 dash minus y1 dash. Similarly, del Z dash, right, del Z dash is z2 dash minus z1 dash, right? Similarly, del T dash, that is given by t2 dash minus t1 dash, right? Hope you have understood this. Now you see, according to the Lorentz transformation, according to Lorentz transformation, del X dash, then x2 dash minus x1 dash, x2 dash is given by gamma into x2 minus v into t2, right, v into t2, then minus, and x1 dash is given by gamma into x1 minus v into here actually that should supposed to be t1, actually t1 in this case, because you see, according to the Lorentz transformation, we know that x dash is equal to gamma into x minus v into t. That's what we know, right? This is according to Lorentz transformation when it is moving, this second frame is moving along x-axis. Okay, then x y dash and y dash remains y and z dash remains z. So hope you know these things, right? That means variation taking place along y-axis, x-axis only. And this gamma is nothing but here root over or you can say 1 by root over 1 minus v square by c square, right? So if you simplify these two, here on taking gamma common, then you're gonna get x2 minus vt2 minus x1, then plus, on removing this bracket, this minus and this minus gonna be plus, right? Then v into t1, that's what we're gonna have, and taking just doing a little bit of arrangement here, x2 minus x1, then from these two terms we're gonna take v common, minus v common actually, minus v is taken common, then we're gonna get t2 minus t1 within bracket, right? So now you see, this is nothing but your del x and this is nothing but del t, right? Hope you have understood this. So we can write that del x dash is equal to gamma into del x minus v into del t. That's what we can write. And according to Lorentz transformation, and we know that here you see t dash is equal to, t dash is equal to gamma into t minus vx by c square. We know this, right? This is according to Lorentz transformation in case of time, right? According to Lorentz transformation. So if we used here in order to find del t dash, so we know that del t dash is nothing but t2 dash minus t1 dash, right? So if we use this transformation for time, then t2 dash will be given by that gamma into t2 minus v x2 by c square. That's what we're gonna have, right? And similarly, t1 dash minus t1 dash, that's gonna be equal to t1 minus vx1 divided by c square. That's what we're gonna have, right? Hope you have understood this. Now you see, let me simplify this. How to simplify this? First take gamma common. Okay, first let's take gamma common. On taking gamma common, and within bracket we're going to have t2 minus t1, then on taking minus v by c square common, we're going to get x2 minus x1. If you simplify, then you're going to get this. Okay, so this is nothing but del t and this is nothing but del x. So that's why we can write that del t dash is equal to gamma del t minus v by c square, or you can write v into del x by c square. So that's what we're going to have. And as you see, y dash remains y and z dash remains z. That's why here we can say del y dash, that's going to be del y, and del z remains del z dash remains del z, right? So hope you have understood this. And let me copy this transformation and let me go to a new slide. Okay, let me first copy this transformation and let me go to a new slide. So here is the new slide and these are the transformations we have taken. Now let me take the time as well. Sorry. So here you see, and these are the transformation we have got till now, right? So just let me adjust these things. Okay, and now we can prove that space-time interval is invariant under Lorentz transformation. We have already taken the help of Lorentz transformation, and now you see we have got del s this, as I have already mentioned earlier, that del s dash square is equal to this, right? So now if we apply those transformation, if we need to show that this is going to be equal to del s square, okay, then it will be proved that space-time interval is invariant under Lorentz transformation. So here you see, so del x dash, let us put this value here. Okay, so using the above transformation we're gonna get gamma del x minus v into del t, then del y dash remains del y, so we can put del y, and del z dash remains del z, so let's put del z, and minus c square, and del t dash is this, so here we can write gamma square del t minus v del x by c square and whole square. That's what we're gonna have, right? So here, as we have del x dash square, so there should be a square and this should be a gamma square, right? This should be gamma square. Now from this two we're gonna take gamma square common. On taking gamma square common within bracket, what we're gonna get? We're gonna get this, just let me write here. Inside the bracket we're gonna get this, and then we're gonna get c square minus c square into this term. Here you see this, so we're gonna left with this, and the remaining terms are del y square plus del z square. Now let us expand these two terms. Okay, then what we're gonna have here, if we expand this one and this one, then we're gonna have here, just let me write directly. So this result we're gonna have, then remaining terms are del y square plus del z square. Okay, what we have done, we have expand this using a minus b whole square formula, and we have got it, this one, right? And expand it we using a minus b whole square, then we have got this result, right? So hope you have understood this. Now let's multiply c square with this one and this one, right? So hope you have understood this. So this is same term, so if you multiply minus c square with this, then this one will be cancelled, right? And this minus will be plus, and if you multiply this one with this, then it's going to be minus c square del t square, and if you multiply minus c square with this, then it's going to be c, this one will cancel this one, it's going to give you c square, right? And this plus sign will be minus, right? So hope you understood these things, very simple, right? So what we're gonna have now, so we're gonna get this result, then the remaining terms are, just wait, let me write it properly, and the remaining terms are del y square plus del y square plus del z square. That's what we have got, right? So here you can see, just give me a second here. Okay, here 2 del t v into del x, here also 2 del t v into del x, so these two terms cancels, one is positive, other is negative. And here you see, from this term and this term you can take del x square common. Okay, if you take del x square common, then what you're gonna have, you're gonna have this gamma square within bracket, we're gonna get del x within bracket 1 minus b square by c square. That's what we're gonna have. And from this term, So you can write these two terms like this: minus c square and minus c square del t square plus you can write c square into v square by c square. Also you can write this way: v square del t square by c square. C square cancels, so again you're gonna get this term, right? So you can write that way. That means what I have done, I have written this term first, then this term second, but I have multiplied c square with both the numerator and denominator. You can assume that way, right? So now from here, if you take this common, minus c square del t square, then here we're gonna have minus 1, and here we're gonna have what we have done here. So on taking minus common, so this is gonna be plus 1 actually, right? As I have taken the minus 1 common, minus c square t square common, and this plus gonna be minus, right? On taking minus sign common, this sign will be changed. So here we're gonna have c square, not c square, this c square is taken common now, and t square is taken common now. So we're gonna have v square by c square, right? So what term is taken common? C square into t square with this minus sign. So here also c square into t square. On taking minus common, this minus will be this plus will be minus, and this minus become plus. Now this becomes plus because minus is taken outside, right? So hope you understood this thing, very simple, right? So now let me clean this part here. Okay, so that's what we have got, and the remaining terms are del y square plus del z square. Now let me go to the next slide and let me copy this last result, last step. So here you see, so this is the last step we have got. This is nothing but what? This is nothing but del s square, right? So now let's take this common, right? And gamma square, we know we have got gamma is equal to 1 by root over 1 minus v square by c square. Gamma square is square of this, and if you take this common, then what you're gonna get? Into 1 minus v square by c square, right? And within bracket we're gonna have del x, sorry, I forgot to give the square here. Let me go back to the previous slide. So that should be square. Okay, so x square 1 minus v square by c square, this term is taken common already, del x square minus c square del t square plus del y square plus del z square. That's what we have got within bracket here. So now you see, squaring this, the square root will be removed. 1 square remains 1 square remains 1 square. So 1 minus v square by c square into 1 minus v square by c square. So this 2 cancels, right? This 2 cancels, and within bracket what we're gonna have? Del x square. Let me rearrange the term, del t square. That's what we have got. And so now you see, let me copy this. So here is the result, and this is nothing but del s square. This is nothing but del s square, right? So here we have got that del s dash square is equal to del s square. So that means what we can say, that space-time interval under Lorentz transformation is invariant. Right? So this is proved. So hope you have understood this. So thank you for watching. See you in the next video. Just pause the video and take the note. Okay.